All right, here we are. This is where we ended video number 2 of OpenMP. Let's go on. Okay, so imagine this. I say pragma OMP parallel 4, and what I'm doing is I'm adding things up. Maybe I'm doing a numerical integration, and so I'm summing things. I'm computing things, and I'm summing them. And the fact that I declared this inside the for loop automatically makes it private. So every thread has its own partial sum, but they are sharing some because we want to produce um, this overall sum at the very end. Okay, well, remember the idiosyncrasies of the scheduler. The assembly code would probably look something like this. For this, load sum, add the partial sum, store it back into sum. Okay. But what if right here the scheduler comes in and swaps this thread out? Well, the sum is in the accumulator, but by the time this thread gets back to running, that's the sum has changed because other threads have modified it. And so it's holding the wrong number. Okay. And this is a problem. And it's non-deterministic because every time you run it, it will mess up, but it'll mess up in a different way. I did a trapezoid integration example, and there's a note set called trapezoid, and it goes into this in more detail. But I did a numerical integration where the answer should have been exactly 2.0. And I ran it 30 different times. And the code was essentially this. Well, I got 30 different answers. And notice if the answer is 2.0, this but these are bad answers and they're not even consistently bad. They're bad all over the place like that. So yes, definitely you want to take a look at the trapezoid note set because it talks about how to actually do this so that you get the right answer. Synchronization. If you are trying to make sure threads don't interfere with each other, there's a number of ways of doing that, but the typical one we use the most is called mutexes, mutual exclusion locks. Okay. And what we do is we initialize the lock. And so there's a variable type called OMP underbar lock underbar T, T for type. And we initialize it. And then any piece of code where we don't want another thread to get in there and change something while we're changing it, like sum equals sum plus partial sum, we would set the lock. Now, if a thread comes along and executes this instruction and the lock is already owned by another thread, the second lock will or second thread will just block. It'll just stop and wait until the first thread releases the lock, OMP unset lock, and then it will go on. Okay, so this is how you do that. You keep other threads out of certain key parts of code until your thread is done with them. There's also a pragma called critical, and whatever code you put after this, either one line of code or things in a curly brace, it will restrict all threads from getting in there. This is a little more heavy-handed than the mutexes, but still pretty effective. Pragma OMP single, the code that comes after that, either one line of code or a curly brace block, only one thread will go in there. The others will skip around or well, will wait at the end of it. And the reason for that is say you're doing something like reading a data file. Well, you don't want all threads reading the data file. You only want one. And so that reading a data file is a perfect thing, or printing something out is a perfect thing to put a pragma OMP single around. And barrier. That creates a spot in your code where all threads have to come there before any of them can go on. Typically, it's after you've computed something, and the next step is going to be I need all the somethings to be computed before I can move ahead. This is an example of the synchronization. So here is the lock type, and I'm going to call it sync. I'm going to initialize it at the start of the program, and then If thread 0 is when it needs to, it's going to set the lock, execute some code, then unset the lock. If it does that and then thread 1 comes along and it tries to set the same lock, thread 1 will block. It'll just stop and wait for that lock to become unset, and then it will go on. So for things like, well, like the push and pop example in the parallel background notes, that's a perfect place to do this kind of synchronization because both the pointer and the value have to be set together. You don't want one like you don't want the pointer changed and then the value changed later. Yeah. Okay. When we talk about functional um, decomposition, we're going to get into this in a bigger way. But supposing you want to parallelize pieces of your code, but you don't want, they're not part of a for loop. How would you do that? Well, it's easy. These are called sections. And what you do with sections is you say pragma OMP parallel sections, and that creates the thread team. And then pragma OMP section, that peels off one thread from the thread team, and it starts executing whatever code is in here. Pragma OMP section, that peels off another thread from the thread team, and it executes whatever code is there. Okay, and so however many threads you typically have that many OMP sections, and then they all synchronize with an implied barrier right here. So this is how to get different pieces of your code running simultaneously, but they're not inside a for loop. And this is very handy. So let's say we had one thread and we executed that section code. Well, they would run sequentially. It would still work, but there's no benefit of parallelism. Let's say we told it we wanted two threads and had three sections. Well, section 1 would run, section 2 would run, and whichever one finished first, that thread would run number 3. But sections are at their very best when you have the same number of sections as you do threads. And so now they can run together, and this is the overall fastest execution time you can get. Yeah, this is what we'll do when we talk about functional decomposition is however many things we have in our simulation, we'll set the number of threads to that. And, well, we've got one thread that's sort of watching over everything, and maybe one thread that's simulating the animals, and another one that's simulating the plants. This is a great use for sections because now each one of these functions is running independently. Now, they just have to watch out for each other, that you might throw some barriers in there, but it's a really, really good use for sections. I think you'll like this. I think you'll like the functional decomposition project. All right. We put this in the notes in the beginning. I'm going to put it again. If you ever get this error out of Visual Studio, it's hard for me to think of anything more cryptic than that use of English. But here's what you do about it. So yes, you can make that go away. Okay, another potential compiler problem. And the standard error, and I always do, if you are, um, so say you pragma OMP parallel for, let's say you're in the for loop and you do an fprintf to standard error. Well, in G and G++, standard error is an actual variable. And so, of course, you have to print to the same standard error for all threads. It's a place to print to. And so you correctly say shared AB standard error. Okay, but that only is true for G++ and GCC. If you then take this code over to Visual Studio, do not put standard error in the list because standard error is a macro. And that just greatly confuses the Visual Studio compiler. Like, why are you trying to share a macro? Okay, and you'll get this message. So yes, and it'll say error, syntax error, left parenthesis, and you have no idea what that means because you don't have any left parentheses in that part of the code. That's what it means. If you're on Visual Studio, do not put standard error in the shared list. If you're on GCC, G++, you have to. Okay, so there we go. There's the more detailed dive into OpenMP. We have a couple of OpenMP projects, and this will tell you everything you know to actually go do them. Go have fun.